Welcome to Calculus. I'm going to work through some examples out of 2.6. I'm going to start with example in the book on page 150. So if you're looking for some extra examples, this would be a good place to watch me work through them the way that I typically do them and talk through them. It's not drastically different than the book, but hopefully it'll be helpful. So this is on page 150. That is a thick font there. See if I can size that down. Okay, page 150, example 2. That's better. So it says, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 2 feet, or when the radius is 4 feet, at what rate is the total area of the water, disturbed water changing? So we're looking at the variables r and the variable a of a circle, where r is radius. So what you're thinking is, what is a relationship between a, area of a circle, and r, radius of a circle? Well, this is great because we have a formula for that. It's pi r squared. So we're probably going to need that. In fact, if we were to, well, before we get to that, let's look at what else we know. We are given, it says that the radius is increasing at a constant rate of 1 foot per second. So that's not r is 1 foot per second. That is the change of the radius. So we write that. This is, you can get used to seeing this as dr over dt. The radius is changing with respect to time at 1 foot per second. Additionally, that's something we know, and you see the question is saying, what is the rate, at what rate is the total area changing? So we're looking for the rate of change of the area. So I like to write this way. I put equals question mark, and I always write when, and they give you some constant. In this case, they say when r is 4. And the reason they have to tell you that is as r increases, the rate of change of the area is going to increase, because if the radius keeps changing at 1 foot per second, the area will be increasing more and more and more. It's accelerating. So how are we going to do this? Well, we're going to take the derivative of our equation. So we're going to do d over dt. We're going to take the derivative of our equation with respect to t. So the derivative of a, what is that with respect to t? We don't know, because we don't really know what a is with respect to t. So this is in a kind of an implicit differentiation, kind of a chain rule thing going on here. We're going to say the area of a with respect to t is the area of a with respect to t. Pi is a constant, we can just put it out there, and the area of r squared with respect to t is 2r times the derivative of r, which we don't know what it is in terms of t. So we write dr over dt. But when you look back at what we're looking for here, we want this. So it's good that it's in our equation. We know this, so it's good that we're going to have a place to put it. So we don't know what this is, but we can solve for it. And r is, we said here, 4. And that 4 you can't plug in the beginning. It's tempting to plug it in right here. But if you did, you'd be done, right? You'd say a is 16 pi. That would be wrong. That is the area when the radius is 4. But we want to find out not what the area is. That's an algebra problem. We want to find out how quickly the area is changing. That's the calculus problem. That's a really bad 4. Sorry, let's try that again. And then dr over dt is 1. So we got to use that, and we got to use that. R is 4, dr over dt is 1, and we're done. So the area is changing with respect to time at 8 pi, whatever that is. And the units, what would the units be? Area is some units squared. We're working with feet, it looks like here. So it's going to be square feet but it's per unit time, so it's per second? Yeah, per second. So that would be our answer on this problem. And I don't really know what 8 pi is, 25 or something like that, but we'll leave it as is. Okay, I'm going to do one more. Well, I'm going to do one more problem on this video. Okay, if you'd like to see another on the basic level, I would look at example 3 in the book. I'm going to move on to a more medium. This is kind of maybe a medium level. This is example 4. Example 5 and 6 kind of go more into the hard level, which we'll cover more in class later. Okay, so this is on I'm doing page 152 now, example 4. This is about an airplane flying directly over a radar tracking station. And it looks like this. Kind of the diagram that the book draws for you. Looks like this. Airplane is here. I'm not going to even try to draw on it. Well, I guess I am trying to draw, but I know it's not going to look good. There's my airplane. Here's the radar tracking station. They have some cool satellite things there, but I'm not going to try to draw that. This, of course, is the ground level. And if you want to measure the altitude of the plane, we always measure altitudes perpendicular to the ground. And you might notice right triangle, what do we do with right triangles? Should be thinking about that. This they call X, this they call S, and this is a constant 6 miles. So the plane is flying level at 6 miles in altitude, which is great. That constant we can set there. So there's a couple of givens here, as I said. If S, it says here, is decreasing at a rate of 400 miles per hour, when S is 10 miles, what is the speed of the plane? So what are they saying? When S is decreasing at a rate of 400 miles an hour. So it's not saying S is that. It says S is 10, but it's saying S is decreasing, and even the units kind of give it away. It's ds over dt. They say miles per hour. I'm going to write it this way, just so we know what we're doing here. And there's a key word, decreasing. So this is negative. They asked for the speed of the plane. The speed, and which way is the plane heading? The plane is traveling west, I guess you could say. It's traveling horizontally. So the speed of the plane really is the rate of change of x. So you kind of had to deduce that from this problem. So we're looking for dx over dt. And in this case, it says speed, so we can assume it's positive. If there's an issue with positive, negative, we can make it positive. That's what they want. And they said do that when, what do we say here? S is 10 miles. Now, this is, yeah, that should do it. Okay, so we want to figure out what is the relationship between 6 miles, the x, and s. Is there some equation we know that we could put all these together? Hopefully you're thinking of it. It's not trigonometry, it's simpler than that. The Pythagorean theorem is right. So we know, let's just erase that whole thing. We know that x squared plus 6 squared equals s squared. And before we take the derivative, it's always wise to see if you're going to get something you don't want. Like if you take the derivative of x squared, you're going to have a dx over dt. But we want dx over dt, right? Because right there, you need that. If you take the derivative of s squared, you're going to have ds over dt. We want that. So this is good news. So I think we're actually in good shape to take this on. The derivative of x squared is 2x, but then we don't know what the derivative of x is with respect to t, so we put this dx over dt, which if we didn't have that, we wouldn't have to be able to solve this problem. So that's great news to have that there. The derivative of 6 squared is 0. That's just 6. That's just 36. So that's good. And the derivative of s squared is going to be very similar to what we did with x squared. Now these 2's are going to cancel, and we don't have a whole lot here. We have x dx over dt plus s ds over dt. And by the way, that plus 0, if that was plus 1, those would not cancel, but the 0 is doing nothing, right? So, alright, we just plug in, we're ready to go. So let's see. We'll plug in for x, then we'll plug in, we don't know what dx over dt is. Then we'll plug in for s, and we'll plug in for ds over dt. Piece of cake, right? S is 10, ds over dt is negative 400, and x, we didn't get x, did we? Did we do something wrong? Did we miss something in the reading? No, this is a thing that happens from time to time, where they didn't give us x because they didn't really need to give us s. X. Remember they said that s is 10 miles. Now let's make a little sketch of this at this instant. So at this instant, that's 10. So what is x? X is 8. That's a Pythagorean triple. If you want to check that, you can. But it's great knowing Pythagorean triples. We can just put 8 there. And if you do that, we'll have, what, negative 4,000 on the right divided by 8, and you get negative 500. Now, remember what we said. So this will be miles per hour. We said that we want speed. Velocity can be negative, but not speed. It doesn't matter. It's going left. It's not negative. It's going 500 miles per hour. So I'm going to just write that down here and put a big box around it. Miles per hour. And if you want to put mph at that point, you could. But hopefully those examples help you a little bit. And keep working at these, keep practicing. One of the key things is write out what you know, and try to figure out what equation relates them. Take the derivative before you plug in constants, unless, like this 6 here is a constant that's not changing. The length of a ladder or something like that is not changing. So you can plug those in. This s here changed, right? It was decreasing over time, so it's changing. So we could not plug that in until after the derivative. That's the key too. So these are difficult, but keep practicing at it, and I think you'll get it. Have a good day. See you next time.